Welcome to our lectures of NPTEL lectures. Today we shall continue our new topic, that is UPFC. We have discussed in details of UPQC, that is for the solution of the mainly for the distribution level, and there is a power quality is the issue. Now we shall connect UPFC essentially in the transmission level, where flow of power in the level of the megawatt required to be handled, and see that how it is does principle of operations will be the same as this UPQC. So, of course, this abbreviations of UPFC is not quality, rather flow. So, unified power flow controller. This concept was proposed in 1991 by Akagi and all. UPFC was devised for the real time control and dynamic compensation in AC transmission system. So, it can, and it is very versatile device. We will see that it can actually control the power and control the phase angle. It got all the solution you require. UPFC is able to control simultaneously or selectively all the parameters. For this I was trying to say that it is essentially a panacea almost for the power flow in transmission line, that is voltage, impedance and the phase angle. We have studied, we have seen the series injection, there we will try to control the impedance or the inject the series voltage, and thereafter we have a shunt compensations. We can have a voltage source solution as STATCOM or actually the SBC solution, and also we have seen the power angle regulator, we try to control the phase angle. It is the combination of all. It can independently control thus both the real and the active power. Active power cannot be controlled by the shunt compensation, and same way actually the voltage regulations, all those things, series compensation is better in that way because it can control the flow of the active power. So, here it can, but series cannot independently control the flow of active and reactive power. Here it is possible to decouple the flow of the active and the reactive power by this UPFC. And thus UPFC of the fax devices is essentially the STATCOM is in shunt path, and we can model it as SSSC in the series part. So, in the practical cases of implementation, UPFC consists of the two voltage source inverter, as we have seen in case of this actually QC, same for the UPFC. So, this was basically the series part, and this is a supply transformer. It will inject the voltage in series with the supply and depending on the different phase angle, and this is basically the shunt part of it, and since it is connected in the transmission network. So, rating of the switches is quite low, we require a coupling transformer to step down the current level, and you have a measured variables, that is actually the voltage, power, V, P, Q and delta. So, we have to have a parameter setting for all, and accordingly control setting will be there. We can actually set VREF, that is a voltage mode control. You can set in impedance mode control, we can set sigma mode of control, and we can set reactive power mode control. So, there is a different mode of operation that you can choose from this UPQC. So, what essentially the UPQC is a back to back converter level as converter 1, that is shunt, that is the right portion of it, and the converter 2 in series in figure are operated from common DC link provided by the DC storage capacitor. So, instantaneous difference of the power has to be fit through the DC link. As indicated before, the arrangement function as ideal AC to AC power converter in which the real power can freely flow in either direction between two AC terminals of the converter, and other converter can independently generate or absorb reactive power at its own AC output terminal. The converter 2, that is basically a series, it acts as a triple SC, provides the main function of the UPQC by injecting the voltage PQ as desired by the different mode of operation with the control magnitude PQ and the phase angle rho in series with the line via the insertion transformer. The transmission line current flow through its voltage source, resulting in reactive and the real power exchange between the UPQC and the UPFC and its AC system. The basic functions of the shunt converter is to supply or absorb the real power demanded by the series converter at the common DC link to support the real power exchange resulting from the series voltage injection. Similarly, shunt converter can also generate or absorb controllable reactive power if it desire, thereby provide independent shunt reactive compensation for the line. Thus, shunt converter can be operated as reactive power exchange with the line impedance of the reactive power exchange by the series converter. There can be no reactive power through UPFC DC link. So, that is something we require to understand it. So, we can operate UPQC in a different mode. One is basically the voltage regulated mode. It is just like a tap changing transformer. We say this circle as a sphere of influence or the circle of influence, and it will have a magnitude of 0.5, where V square by x is considered to be the 1 per unit. So, you can compensate within this anything in a sphere of influence. Let us see that how it will compensate the voltage sag limited to 0.5 and the minus 0.5, swelling of minus 0.5. UPFC can fulfill these functions and thereby meet multiple control objective by adding the injected voltage PQ with the appropriate amplitude and the phase angle. It can inject any phase and any angle within this circle. UPFC with voltage regulation with continuously variable in phase and the anti phase voltage injection is shown in this figure for PQ equal to del V, where it is in phase, thus rho equal to 0. This functional is similar to the tap changing transformer having infinitely small step change. So, you can inject very precisely, and thus content of the harmonic is greatly reduced. You do not have a problem of the harmonic. So, you can inject any value with the voltage in phase with the UPFC. Similarly, series reactive compensation, you want to compensate VQ, and thus you inject the voltage perpendicular to the current. So, this is the current I and you inject the voltage perpendicular to the current either minus Vc or plus Vc, or some books also refer as a VQ. So, where this PQ equal to VQ and we make it Vc here or slash Vc is injected in quadrature with the current, because I have chosen this nomenclature because we have actually discussed that as Vc in triple SC with the line current. Functionally, this is similar to the series capacitance, and the inductive line compensation is attended by triple SC. Students are requested to actually refer our discussion in SSSC. You will find that it is a similar thing, that it can be achieved by also UPQC. The injected series compensation voltage can be kept constant if desired, independent of the line current variation, or can be varied in proportional to the line current. This is the line impedance. Phase angle regulation. So, it will change the sigma and it will keep the magnitude same, where PQ equal to V sigma is injected with an angle relationship with respect to that achieves the desired Vs. Thus, UPFC can function as a perfect phase angle regulator as discussed here. Also supply the reactive power involved in transmission line angle controlled by internal var generation, mainly by this series compensator. So, for optimally use the rating of this UPFC, we may require to take all those parameters into the account. For example, in this case, let us consider that you require to inject the value PQ and you inject some voltage in series, that is del V, you inject some voltage in quadratures, that is Vc or Vq, and thereafter some portion as PUR, that is power angle regulator, and ultimately you get it, and that gives you the optimal compensation, because the rating actually been reduced maybe, and we can find it out what should be the level of del V, Vc and actually the V sigma. So, that is possible here. Multifunctional power flow control executed by the instantaneous terminal voltage regulation, series capacitance, line capacitance, and the phase shifting by del V sigma, where actually the functional capacity is unique for the UPFC, mainly you optimize the rating here. No single conventional equipment has the similar multifunctional capacity. If you wish to achieve it by the different fax devices, then you require a tap changing transformer for this part. In this part you require actually SSSC, and in this part you require a PAR, power angle regulator. So, all those tasks can be combined and can be successfully executed by UPFC. That is one of the unique advantage of the UPFC. So, how power flow, because we see that it is a quite versatile device, how does this power flow, and it is power flow can be controlled. The real and the reactive power transmission versus the transmission angle characteristics, we should have to go back to our two machine model. The characteristics of the simple two machine system for uncompensated system, which already discussed in the series shunt compensation. That same will be the takeaway, because essentially the which mode of operation you select. If you go that, if you select this mode of operation, this is basically the tap changing transformer, that equation will come into the picture. If you take this mode of operation, then we have to say that actually the SSSC's operation, and if you say V sigma operation, that will be actually PR operation, and accordingly the rating will change. So, when it is combined, so we can express in this following way, that is Vs, that is injected voltage is PQ, that this is a combination of all the three type of compensation that can be achieved by the UPFC minus the sending end voltage by Jx. So, we can see that for the compensation system with the real power, that is now is a function of rho and delta. So, it is V square by x sin delta, which is the uncompensated one, and thereafter you have a compensated one where V by x PQ cos delta by 2 plus rho, where v square by x is 1, we generally consider v pq by x as 0.5. So, this is something we will assume and we will consider this is the radius of the circle, and that is your sphere of influence of the this kind of UPFC. Similarly, for the compensated system, so you can see that actually you have a huge term to monitor. So, you can play with the rho and also you can play with the VQ, and thus you can have a quite big range of controlling of this P. And similarly, we go back to the equal area criteria and establish that its transient stability and it can damp out the power angle oscillation, all those things. So, that will be an extension what we have done in series. We just actually we cannot actually now discuss it, but student can take it that reference also here. So, now so what happens for the similarly this value q delta rho will be given by v square by x 1 minus cos delta by x, that is uncompensated one, plus or minus. So, another term will come, that is v square by x pq sin delta by 2 plus rho. So, we can see that we can inject real and the reactive power control between minus v x v p q by x to plus b q by v p q by x. Generally this magnitude we consider to be 0.5 per unit. So, thus considering this value to be 0.5 per unit, this is the uncompensated line for real power and this is the compensated line for real power, and you can see that you can send power even at 0 delta, as well as it can be you can send the power back, that is also very important aspect of it. Similarly, this is the uncompensated power for your reactive power. So, you can increase by the sphere of influence of 0.5, where this is the sphere of influence. Now, the phasor diagram defining the relationship of Vs, Vr, Vx the voltage phasor with x and inserted phasor PQ. Now, essentially this is your receiving end voltage and this was your sending end voltage, and you have injected this voltage PQ, thus effectively this becomes a new voltage, that is V effective sending, and thus there will be a new delta, and thus you have injected actually this value Vx. So, the inserted voltage phasor Vq is added at a fixed angle voltage. The phasor Vs produces the effective sending in voltage, that is Vs effective is given by Vs plus Vq. The angle rho PQ is varied over the full 360 degree. You can inject at any point, that is this is the rho, it can be actually injected anywhere in this sphere of influence. So, it can be any angle 360 degree range. The end of the phasor VQ becomes along the circle with its center located at the end of the phasor Vs. So, that is something we require to do that. So, that is what happened. By doing it, what will happen? Let us consider that how this power changes. You know, this is the delta. So, this is the P and this is actually the per unit value 1. You can actually increase the value of the P to 0.5 and at delta it can go to very high value. Similarly, this is basically the QR. So, QR will be like this, and this was the uncompensated one, and you can make it a compensated one by this way. The rotation of the phasor PQ with an angle rho PQ modulates both the magnitude and the phasor angle Vx, and therefore, both transmitted real power P and the reactive power Qr vary with the angle rho PQ in a sinusoidal manner. So, it will vary like this. This is basically the plot of rho. So, it will change like this. The UPFC can achieve the independent real and the active flow of the power through the transmission line. That is one of the basic requirement. Let first assume that the injected voltage, compensating voltage PQ is 0. We are not actually injecting any voltage. Therefore, the normalized transmitted power, it is V square by x sin delta. We consider this value to be 1, thus we left with the sin delta, and the normalized reactive power, it is V square by x 1 minus cos delta. So, we left with 1 minus cos delta and supplied by the end of the line, and we actually normalized this value to be 1. So, we have these two curves which we was discussing from the beginning of the classes. So, what happened here? Now, see the locus of it. So, you just plot P in x axis and Q in y axis. So, you can go maximum 1 in case of the real power, and this equations 1 minus cos delta at pi, this value becomes 2. So, you can go to 2 per unit with the real power. So, what happened? This is the mode of operation. Now, the relationship between the real power P delta and the real power Q delta can be expressed in basically a unit circle form, and what happened, Q square delta plus 1 square plus P square delta equal to 1. So, thus you have a center at this point. Now, consider that PQ not equal to 0, then you are actually not, basically you are injecting some voltages, and therefore, the real and the reactive power exchange from the uncompensated values of P delta and the Q delta as a function of the magnitude of the PQ and the angle rho is injected with the phasor, and that value we shall tell that it is PPQ, and thus this actually this circle will shift. So, as shown in the equation in slide number 11, the boundary of the attainable voltage region P delta rho and Q delta rho is obtained from a complete rotations of the phasor BQ with the maximum magnitude of PQ max. From the power equations, that this control region is a circle with a center defined by the coordinate PQ delta and the Q delta with radius VPQ by x that equal to 0.5, generally chosen. Thus, what happened? The boundary circle can be described by the following equation, that is P that will modify in case of the you are injecting the value PQ, PQ is non-zero. So, P delta rho minus P 0, that is the uncompensated power square, plus Q delta rho minus Q uncompensated power, that should be equal to the your V by VQ max by x square. The circular current region defined the above equation will be shown. So, we shall take different values of compensation, delta equal to 0, delta equal to 30 degree, delta equal to 90 degree, and see that what happens. This is a case of delta equal to 0 degree, and you see that there is a unit circle and this is a controllable region, and thus what happened, this is a case of the line where actually PQ is 0. So, you will have this line, ultimately this circle will will move like this if you change the value of the delta. Similarly, what happen if you make delta equal to 30 degree, so the real power will be 0.5 and imaginary power you can calculate. So, it will shift at this point and this circle will be actually coming like this. This is a line actually the PQ equal to 0, and this is a line actually PQ negative, and this is a line equal to actually the BPQ is a positive. So, ultimately this is the amount of the compensation you will achieve for delta equal to 90 degree, you will be here, and delta equal to 90 degree you will be here. Similarly, we can make it for the 60 degree. So, this origin will shift to for accommodate value of the 60 degree, and then you see that how you are changing its locus. So, ultimately your real power value can touch to the little less than 0.15 because you can go to that level. So, your compensations point increases. Typical case is your 0.9 delta equal to 90, your origin will come at 1 and definitely you can compensate that, you can make this the real power compensation 0.5 to minus 0.5. Similarly, reactive power also 0.5 to minus 0.5. So, this is a controllable region for delta equal to 90. Thus, what we can control it. So, let us understand this zone of control, and these are the takeaway. So, with the suitable control, UPFC can cause series injection voltage vector to vary rapidly and continuously in magnitude and the phase angle as desired. It is not only able to establish an operating point within a wide range of possible P and Q condition on the line, but also has inherent the capability to transmission line rapidly from one such achievable operating point to other. The control of the UPFC is based upon the vector control approach. The term vector instead of the phasor is used in this section, represents a set of instantaneous phase voltage, phase current and the sum 0. So, this is actually the zone of operation and control of the UPFC. We shall continue our next class with the UPFC with its different mode of operation and control. Thank you for your attention.